Hey guys, I just want to start off today real quick with a warning. Joe's downstairs watching the NFL draft, so if he gets loud in the background, sorry about that. I asked him to be quiet, but who knows. Today what we're learning is Goal 4. We're in Chapter 12, Section 2, and we're basically looking at evaluating limits of polynomial and rational functions at infinity. And we've already looked at this graphically and numerically. Now we're just going to look at it from an algebraic perspective. So just a quick review. If we're talking about the limits for polynomials as x approaches infinity or negative infinity. So remember, this is end behavior. We're talking about the right end and the left end. If you have an even polynomial, so that means the highest power is even, such as x squared. What we know is that if the leading coefficient is positive, which means the coefficient of this highest powered term is positive, then the ends are both going to be going up. Remember, for even, both ends have to be going the same direction. However, if you have a negative leading coefficient, such as negative 2x squared, that flips our function over the x-axis, so now both ends will be going down. So both limits will approach negative infinity. These will always be the same limits no matter what your even polynomial is. As long as it's an even power and a positive or negative leading coefficient, these are always your limits. Next, let's talk about odd polynomials. So this is like x cubed, or wherever the highest power is an odd number. If the leading coefficient is positive, then that means the left end will be going down and the right end will be going up. So this will always be your two limits to describe the end behavior. However, if the leading coefficient is negative, such as negative 2x, then that means that it flips over the x-axis, so it goes up on the left end, down on the right end. So these are always your limits for positive leading coefficient odd polynomial. These are always your limits for a negative leading coefficient with an odd polynomial. So let's try these out. It says, example 5, the limits of polynomial functions at infinity, evaluate each limit. Let's look at A first. So it says the limit as x approaches negative infinity of x cubed minus 2x squared plus 5x plus 1. Sorry, minus 1. Basically, what you have to do is figure out what's the leading term here. Make sure it's in order from descending power. So we're looking for the highest power. Our highest power is x cubed. So we know that this would be equal to whatever the limit is as x approaches negative infinity for x cubed, since it's the highest power. It's an odd power, and it's a positive leading coefficient. So we know that means that it's going to be going down on the left, up on the right, such as a function like x cubed. So it's asking us as x approaches negative infinity, so that's talking about the left end. As x approaches negative infinity, our y value is going down, so the limit of this function on the left end would be negative infinity. Next, this function for b is not in a correct order. It doesn't have the powers in descending order, but you still need to look for the highest powered term. So this is an even polynomial with a negative leading coefficient. So we know that means it's going to look something like this, an upside down parabola. And they're asking us as x approaches positive infinity, so that means we're talking about the right end. We know that this will be equal to the limit of just negative x squared as x approaches infinity. So this would be just equal to negative infinity, since negative x squared would be approaching negative infinity on the right end. For C, our leading term should be 5x to the fourth. This is an even polynomial with a positive leading coefficient. even though it's x to the fourth, it still behaves like x squared. Since it's positive, we know both ends will be going up. And we're looking for the left end. So on the left, if it's even with a positive leading coefficient, we know it's going up towards positive infinity. Next, let's look at the limits as x approaches negative or positive infinity for reciprocal functions. So a reciprocal function is something like this, 1 over x. That's our basic reciprocal parent function. Now, if you look at the graph of this function, you'll see that on the left and the right, we are approaching 0. On the left end and on the right end, our graph approaches 0. Now let's look at 1 over x squared. This graph looks like this. I've already drawn it out for us. As x approaches negative infinity, we're approaching 0. As x approaches positive infinity, we're also approaching 0. It turns out that no matter what the power is, it always approaches 0 on the left and the right ends for any power. So anytime you have 1 over x to any power, it always will approach 0. So that's helpful because we can use these tricks that we learned back when we were talking about horizontal asymptotes. So there are 3 tricks here. So 3 cases. Case 1, the degree of the numerator is greater than the degree of the denominator. This means that the limit would either be negative infinity or positive infinity. It acts similar to a polynomial. So think about it. If you divided this out, because technically this means division, this symbol right here, even though it's a fraction, like a rational function, it means division. So if we divided out this function, 2x cubed divided by 3x squared, that's going to leave us with a positive leading coefficient and x to the first power. So we know that it's a positive leading coefficient, and since it's x to the first power, it's odd. So odd positive leading coefficient is going to look something like that. It could have different curves in the middle, but the end behavior is always going to act the same. We're talking about the right end. So the answer for this limit should be positive infinity. Next, if the degree of the numerator is equal to the degree of the denominator, the limit is equal to the ratio of the leading coefficients. Remember back when we were talking about horizontal asymptotes, we said that the horizontal asymptote is at y equals the ratio of the leading coefficients. This time we're talking about limits, but it works the same way. Our leading coefficients here are 2 and 3. So the limit, it doesn't even matter what end we're talking about. We're talking about the left end here, but we don't really care. Because on both ends, the function will be approaching the ratio, which is 2 over 3, 2/3, or 0.6 repeating. Next, if the degree of the numerator is less than the degree of the denominator, this would be a case where it acts like a rational function, such as 1 over x, because you could go through and do some little algebra trick, which we're not going to go over. Normally we would, but since you're at home alone, it's kind of difficult, so we're not going to go over that. But I'll just tell you that it acts like a rational, such as 1 over x. So the limit is always equal to 0. Okay, let's do an example together. So these are limits of rational functions at infinity. For a, the limit as x approaches infinity for this function. Think about it. If we divided this out, we're going to end up with just 1/2 plus some remainder. And since the powers of the numerators are the same as the power in the denominator, we know we're talking about case 2. So for case 2, it's equal to the ratio of the coefficients, so the limit is equal to 4 over 8, which we could reduce to 1/2. Next, for b, we have the limit as x approaches negative infinity, so we're looking at the left end of this function. the degree of the numerator is less than the degree of the denominator. So we're looking at case 3. Remember we said for any of these, no matter it's the left end, right end, it behaves like a rational. So the function's limit on the left and the right is always equal to 0. Last, part C, we have the limit as x approaches infinity. So we're talking about the right end. And for this function, the degree of the numerator is higher than the degree of the denominator. So this is case 1. And for case 1, we need to kind of look at the division a little bit. So we only really care about the division of the leading coefficients and the leading power, like the leading terms altogether. So if we look at this division, all we care about is 5x to the 4th divided by 9x cubed. And we don't even really care about the numbers. All we care about is whether it's positive or negative and the power, whether it's even or odd. So 5 divided by 9, it's a positive divided by a positive. So I know that the leading coefficient is going to be positive. Next, I have the 4th power divided by the 3rd power. 4th power divided by 3rd power of x would be x to the 1st power. So I know that the 1st power is an odd function. So I'm looking at the case of positive leading coefficient, odd function. I could think of x cubed to represent this. Now I go back to my limit. So I just decided that I'm looking at positive leading coefficient, odd power, and I'm looking at the right end. So if I'm looking at the right end, it's going up on the right. So this limit should be equal to positive infinity. Now, know that you can check all of these answers graphically or numerically on your calculator. However, this is just a different way to look at these functions algebraically and look at these limits algebraically. I'd like you to practice these homework problems tonight using the algebraic techniques that I just taught you. Have a great weekend. Bye, guys.